Welcome to Developer Highlights. Today's topic is building ambitious subgraphs part 2. As last time, I have with me Sebastian Simpson and Ivan Herger from Enzym Finance. How are you guys?
Good. Thank you.
Good, thanks.
Just dive right into it. What topics are we covering?
We are going to talk about performance tips, so fine-tuning performance for your mapping code, your handlers. So improving indexing performance for your subgraph, tricks and some quirks also around performance tuning. Also query performance, how you can build queries, especially when sorting and filtering and scraping data to query that data faster. And then we'll talk a little bit about some assembly script quirks and utilities that we have built and that we are using in our subgraphs for convenience. So utilities for mathematical operations, string decoding, encoding utilities, time utilities, so time ranges, time window operations, especially useful for aggregating data, for instance, price data in predictable time windows, so monthly, hourly, weekly, daily, and so on. Yeah, and as well as some like low-level mathematical operation and utilities that we're using frequently, and array operations, so filtering arrays, things that are not as easy in assembly script, simply because A, there's no package for some of these things, or B, because assembly script simply has some quirks around those things, and especially if you're coming from a TypeScript, JavaScript background with the entire vast universe of NPM packages available at your fingertips, you're going to miss these. So yeah, we've built some utilities around those that I think would be worthwhile to share with the community, and that we are likely also going to publish soon as a standalone package that people can then use for building their subgraphs.
All right. Yeah, let's get started with the performance tips. I'll just start with some simple ones, I would say. So typically, syncing your subgraph can take quite a long time, and if you have done that kind of naively in the beginning, you notice that syncing starts right at the beginning at block 0, basically, and probably your contract hasn't existed for the first few million blocks. So the first and very simple trick is to make sure that you always set a start block field in your subgraph definition file, so that it basically starts syncing whenever the contract or the contracts that you're looking at have come into existence, not before.
What's noteworthy here is, right, that if you have different data sources in your subgraph manifest, it will take the lowest common or the lowest starting block from all of those. And if you forget to define the starting block for any one of your data sources, then yeah, it will start at block 0.
Yeah. There may be one or two other very simple things. Is you should always prefer event handlers. So when you write handlers, write event handlers if possible. Call handlers are much slower, and block handlers are really slow. There are use cases where you will need them, but if you can prevent that, do prevent it. So always look at event handlers. When you have an event handler, make sure that you kind of use that event data as much as possible. So typically there's various parameters that you get from the event data. Make sure you use that. Make sure you don't use contract calls for things you already have. And I think we'll come back to that later also, but often don't do contract calls if you can avoid it. Sometimes you have to do contract calls, but it can be avoided by using event data, but it can also be avoided by cleverly designing your schema. And sometimes you can basically look up things in the database that you will need to kind of that you will need for further processing. And so you can look it up in the database and not do contract calls.
One thing that is noteworthy also for the contract calls, whenever you are indexing events and the data at the time of the event is important, and something that people very often don't realize, in my experience, is that if you make a contract call in your mappings, in your handlers, that contract call is run at the end or at that block number in which your event was run. So the data at the time of the event might very well be different than the data that is returned if you make a call that returns that same information. So, for instance, if you are if you have a simple ERC20 event, not on the ERC20 contract spec, but if your contract that you are indexing emits an event that returns, for instance, the balance of an ERC20 token of a given address at that exact moment in time when that event was triggered, that balance that is returned as part of this event might be different than the one that you'd get if you query, because that is at the end of the block, and the other events, other transactions might have caused the balance to change. So there's not only a performance difference in the two, there's also a potential difference in the data that you get at that point. And we ran into this problem actually quite recently with Chainlink price updates, Chainlink Oracle price updates. And there's, for instance, there can be a scenario where the same Chainlink aggregator, the transaction for updating the price in that Oracle, two of these transactions are included in the same block. And obviously, the price that you index at the time of the event, we had this optimization logic in there that whenever there was already a price update for a given block in our data storage, in our entity storage, we skipped the next update so that we only have like a maximum of 1 updates per block. But now, obviously, we weren't getting or we weren't storing the right price update because a later update actually overrode the price update. We would have caught this if we had made a call on the contract to then afterwards like get the real like end or block end price at that time. But instead we used the parameter, the value from the event. So it's just something to be aware of. It's a performance consideration, obviously, to use events and not calls, but also there are consequences of doing that, right? Yeah, just something that I wanted to raise.
Yeah, good point.
Yeah, so following up on what Ivan said regarding subgraph definition and performance of the different types of handlers. So there's one handler that, or one type of trigger that we didn't talk about yet. You know, we have event handlers, we have call handlers, but we have also block handlers. It's possible in theory to have a handler, a mapping that runs on every single block. In reality, however, this is so slow that under no circumstances do you actually want to do that. Block handlers exist, so I guess bottom line, yeah, block handlers do exist. It doesn't really make much sense to use them in our experience. We haven't come across a use case yet where the performance penalty of using them would be justified. Usually there's a clever way that you can use events of some sort. It would be great, honestly, if there was some sort of cron handler, so block handlers, but for only like every 10th block or so, or every 100th block even. Maybe even not block based or block number based, but rather time based, so that you could, for instance, capture predictable time windowed data about prices, balances of tokens on a wallet, these things. That could be quite useful. There's already an open feature request for that. Yeah, and then yeah, I mean, Ivan already said that call handlers are just really really slow. So yeah, avoid them if possible. You can filter block handlers, but still, like even if you do that, it's too slow to justify, in my opinion. If you have the ability to design, or if you have the ability to influence the design of your smart contracts of your project, then yeah, ask your Solidity developers to optimize the contracts in a way where you can really 100% rely on events instead of having to use block handlers or call handlers for that matter. Event handlers are always preferred. Yeah. So one thing that we didn't actually mention yet, it's actually possible to further limit what events a mapping is triggered on, what events that handler is triggered on. You can in theory limit on the indexed sorry, on the topic 0 of that event signature. That is a possibility. So far, we haven't had a use case for that yet. What we would like to see actually is the ability to further filter on the indexed addresses of a transfer event on ERC20, for instance. But that would require observing, or that will require a feature where we could also specify topic 0 and topic 1 both at the same time, potentially also with the ability to like only requiring one of the two to match. One use case for that would be a generic ERC20 subgraph that monitors all ERC20 transfer events for all assets, but not for all holders, not for all token holders. So in our use case, for instance, in our asset management platform, we are only concerned about transfer events that include one of the vaults that we are monitoring on our platform. So it would be quite handy if there was a way to have an event handler that we could incrementally append addresses, indexed parameters of these event signatures that we are concerned about. And then only firing the event on those. So doing the filtering already on the graph node level before even calling our handlers. That would be quite useful. Maybe to show you what we are doing instead right now. So we have this Vault Balances subgraph. Yeah, what we are doing here is indeed just some optimization. So we are observing every ERC20 transfer event. That's possible by listening to all ERC20 contracts without specifying an address in the data source here. So you see where we are monitoring ERC20 contract ABI at a starting block, which is roughly where our protocol was deployed. In theory, this isn't accurate because you could already transfer an ERC20 token to a contract that doesn't exist yet. If you are going to deploy it at a predictable address, and you know that you could, in theory, deploy the contract after having sent some assets there. But in reality, that's something we happily ignore here, for the sake of performance. So we are starting at that block number, monitoring this contract or these ABIs from that contract for the entire address universe. And then we are listening to all transfer events that conform to this event signature. And then what we do,
just to make sure people are not confused, this is on Koban, and the starting block is is slightly different from the current mainnet.
Yeah, this is for development. This is currently development. Yeah, true. Right. So yeah, what we are doing then is where's the handler mapping? There we go. Handle transfer. So here, since we are not able currently to check or to limit the transfer events that are triggering this handler to only those that we are concerned about, we built in this like this first check. So if the to or the from address of this transfer event is one of the addresses that we are concerned about, so namely if it is here actually, sorry, if it is a volt on the to address, or if it's a volt on the from address, then we continue to index it. If neither of the two is actually a volt, then we just don't listen to that event at all. So we bail out early. That's just for performance, really. So we're not tracking all. We're not storing entities for all events. And then one more thing that we do also for optimization here, because we are monitoring the entire asset universe and or the entire address universe, it's very possible that there is somewhere an event triggered somewhere on the blockchain that has the same event signature, but it's not actually an ERC20 token. So in our function here called ensure asset, we verify if the event was actually triggered on an address that is indeed an ERC20 token. And in order to validate and verify that, we basically check if there's a decimals function on the contract. If there isn't, then we just assume that it's not a valid asset, and then we ignore it. This isn't entirely true for all ERC20 implementations in theory, because the decimals function is not required strictly by the spec. But for the asset universe that we care about, all of the assets that we have in there have that. So this is why we can safely assume this. Also, we check if we can call the balancer function. We're using Vitalik's wallet for that. And if that reverts, if that call reverts, we also ignore that asset. And then for token name and token symbol, we are a little bit more forgiving here. If there is no valid token name or no valid token symbol, we just default it to unknown and store the asset regardless, because also, strictly speaking, token symbol and token name are not required by the spec. So what does this do? We save an entity called ignore asset. And this is also an important point about schema design and performance. Since this logic here runs a bunch of contract calls, we don't want to, like, if we figure that one of these assets that we are getting an event for is not an ERC20 token, we don't save it as an asset, right? But the next time such an event occurs, we don't want to run the same logic again, because we have already established that that address is not an ERC20 token. So we have a entity in our schema, an entity type in our schema that's simply called ignore asset. And this is not actually meant for the consumer to query it. This is meant purely for our mappings to improve and improve performance and optimize our mappings in such a way that if we load, or if we have such an entity stored for a certain address, then we know already that we can safely ignore the transfer event without having to run these checks on the second time we are seeing these events. So that's maybe another hint. The schema can absolutely be used for storing data that the consumer isn't concerned with, just to maintain state or make future calls obsolete by instead storing state in an entity, internal state, so to speak, like state that is not meant for your client-side application, but simply to run your logic. Yeah.
Maybe another point is when you want to get an entity, you can load an entity, so entity.load, which you don't, if you're just wanting to write something into that entity without checking anything, if it's already there, or if without checking any other fields in that entity, then you can create a new entity Then you save it, and if it already exists, it will overwrite whatever you have changed, and if it doesn't exist, it will create it. So it's kind of an absurd command. So only use load if you need access to things that you had already stored in that entity. And then one thing we do quite a lot in our subgraphs is we wrote helper functions for loading or initializing entities, because then that allows us to kind of load or construct entities in different parts of the code in different handlers, and we don't always have to kind of take care about the low-level stuff that need to happen when we create or get or create an entity. And so Sebastian, you're showing this get or create asset function here, which is a good example. So we're basically checking if the asset already exists. If it already exists, if it doesn't exist, we create it, and otherwise we don't need to do anything.
In this case, it's particularly important because when first, like in our subgraph, we have registries for the assets that are supported in our application. So every time a new asset is added to the asset universe, we initialize the entity for that asset that was just registered. And because the only information that we receive from that event is the address of that new asset that was entered, we have to obtain the other information like the decimals for computations on the prices later on, the token name, the token symbol, all of the things that we want to visualize on the front end. And in order to load these, we make calls, on-chain calls. So doing this over and over again, on every time this asset is accessed, would be rather expensive performance-wise. So we have this utility function, as Ivan suggested already, that tries to load it. If it doesn't exist, it tries to create it, and then it returns it at the end. Naming pattern-wise, like usually we call this ensure asset or get or create asset. It's pretty clear what it does. And the same we do with all of the different asset types. So here, asset price. Well, that's a different case where, again, here we load it. If it exists already in that block and there's already a price for that, we return it. Otherwise, we create a new price for that block number. Currencies, well, the same thing. And just about with every entity that we have in our system, we usually have such a utility function that just makes it more convenient to access these entities throughout our code base.
Yeah. So then you don't need to be concerned about the order of in which event an entity is created or updated. You can basically always use that, and if it doesn't exist, it will be created, and if it already exists, it's a very short, very lean call.
Yeah, this goes a little bit against what we said before, where we argued that you should only do load if you really need to. I would argue that for more complex subgraphs, where actually the readability just is improved significantly if you do this, like the simplicity of maintenance or the improvement of maintenance overhead, like by using these helpers, outweighs the minor performance gain you'd get from avoiding the load in this case. Because one thing that is also important here is that load and save are all cached. So doing the same, doing load again over and over on the same ID does not cause this load operation to go to the storage layer again. Instead, this is cached in memory in the GraphNode host environment. And same with save, by the way. So even invoking save several times just writes it to the cache first, and then when your current mapping handler is accessed, that's when it's written into the storage layer at the end of the entire mapping processing. That's when it's done once at the end. So just to visualize, like our handlers are very very simple usually, very little code in those handlers. We just chain a couple of utility functions that receive parameters. So these event handlers are simply doing the routing of the event parameters to the function calls necessary to update the state, right? So usually not a lot of code in these handlers in our subgraphs. I think that's quite considering the complexity of the subgraph, there's not a lot of stuff going on here.
Well, there's a lot of stuff going on, but it's kind of
it's hidden,
nicely
right?
hidden.
Yeah, just utility functions for whenever there's a repeating pattern. For 1 to n relations in particular, if you have an arbitrary sized array property on any of your entities, it's usually good to store that relation with or rather inverse that relation and then derive it at query time. So what this does is, instead of actually, when you are now, let's take this controller proxy entity as an example. When you're saving this entity, you're not actually saving the fee settings or policy settings references to these underlying other objects in these properties. Instead, these have a reference to the ID of the controller proxy. So the controller property on the fee settings interface, let's find that real quick. Here it is. So this one here is instead pointing at the controller proxy, and then through the derived from directive, then instead these point or these are like a reverse relationship to the controller based on the ID of the controller entity that they are referencing. Yeah, this allows for quite nice, convenient access to related entities without all of the overhead of storing these relationships on both ends of the relation. So large arrays are usually an anti-pattern that should be avoided, especially if you don't know the size of an array, or it could potentially become really big. Avoid storing that array directly on the entity. Maybe let's quickly look at our subgraph and show what the derived from does in this case. Right. So here we are looking at our subgraph now in the GraphQL Explorer on thegraph.com. And so if we're loading one controller proxy here, obviously you have the normal relations. For instance, in our case here, to the fund, so you can look at the name of the fund and so on, right? But there's also queryable fields here, like fee settings, that allow us to narrow down our query and actually look at the fees associated with this fund. And these fees are not actually stored as, or these fee settings rather, are not actually stored on the controller. They are stored and referenced back to the controller through the controller property here.
Using the schema to store state, I think that's that can be quite useful. So if you, so what we do, for example, which is very simple, but we just have a counter that counts the number of vaults that have been created. There's a state, and there's the number of funds, and the number of managers, and the number of investors. So whenever the fund is created, we just increase that by 1, so that we can very easily query that number later, so that we don't have to load all the funds later and go through that array and count off that, because that would be, I mean, it's also possible, but it's kind of an expensive query. So we have this state, basically this state where we know the number of funds that so these kind of things. Yeah,
absolutely. I mean, this is a pattern that you'll see over and over again, and that you'll have to use over and over again when you're defining your schema. You have to do much more already on at indexing time than you are used to from traditional apps. You don't have access to custom resolver logic, so you are just left with whatever your schema offers. You can only query that stuff. You can't do aggregate queries. You can't do more logic, custom logic at query time. So everything that your app is concerned about should already be indexed and part of the schema. So any kind of state that you want to track, counting is actually a really good example. So because that's also a really like limiting feature right now. Usually commonly you would want to not only count the entire range of in our case, for instance, funds, but maybe you would want to count all funds that fulfill a certain or that have a certain property set on them, right? So yeah, you can't count and filter with that flexibility at query time. So all of that data already has to be prepared within the schema when you're indexing that data. That's a really good point. Try to design your contract so that you can rely on event handlers purely if that's possible. If you don't have control over how those contracts look, because maybe you're also monitoring contracts that are external to your own smart contracts and simply smart contracts that you're interacting with that you need data from as well, then, well, there are still some tricks and patterns that you could use. So for instance, what we use, we have primitive assets and derivative assets in our asset universe. Primitive assets are backed by a Chainlink price feed. And derivative assets, however, they don't have a event associated with them that we could track and update the price from. So what we do instead is every time we are receiving a price update for one of our primitives, we just trigger price updates for derivatives also as a side effect of that operation. So we are kind of abusing the Chainlink events as some sort of cron triggers to update prices also outside of the scope of that event, if that makes sense. There's actually one thing that I want to highlight also when querying data that is quite handy. So in the previous episode, we talked about pagination and how skip and first is a really bad thing for querying performance. So instead of using skip and first, you should always prefer iterating through a larger data set using filters, right? And then filters with sorting and sorting direction. Here, for instance, we are querying asset prices. And increase the size of that. Here we are querying asset prices for a given asset above a certain time. So the first 10 after, like this timestamp is from 3 months ago. So the first 10 asset prices that occurred after 3 months ago in ascending order. And then the trick here is if you know that it's reasonable to assume that you will have 10 records within, let's say, let's be conservative here, let's say 1 month, you will get at least 10 price updates. Obviously, you'll have much more, right? But if you can limit, however, if you can somehow reasonably assume that within a certain filter range, you will also get these 10 records, then it's quite nice for performance of the query to not only limit the data set you are sorting and filtering on by a lower bound, but also limiting it by a reasonable upper bound. So in this case, that's I think 1 month ago or 2 months ago. So we are assuming that within 1 month we have 10 asset price updates. And then the query is actually much faster than it would be if you did not include this upper bound, right? So this is the most obvious solution for the filtering problem. So you're getting the first 10 updates after that time. But yeah, including the upper bound actually does have query performance benefits. Yeah, I think that's all I can think of right now in terms of query optimization, apart from the stuff that we already talked about last time.
Yeah, let's start with time series data tracking. So we do a lot of time series data tracking. Basically, we have funds that people invest in, so that and each fund has a share price, and so that share price is changing over time with trades that are made with prices on assets that are updated. We track a lot of that data in the subgraph, but not all of the data. I mean, we track all the data that we need to calculate everything ultimately, but we don't do all the calculations in the subgraph because that's not fast enough and it's not scalable. But so what we do track is asset price updates, and as Sebastian said, so we use Chainlink for that. We have quite a big asset universe that we support, and basically there's quite a lot of events coming in with new asset prices. I assume today there have been quite a lot of asset price updates, wrong direction, but still they have come in, I assume. And in order to make sure that, and they come in at random times, basically with every block or every few blocks, and sometimes there's larger time windows where nothing happens. In order to make sure that we can use those price updates in a good way, we define time windows, and we store those asset updates. Either we store all of them or we just store a few of them based on the on time windows. So for example, we define hourly time windows, and then whenever there is a an asset price update coming in a certain time window, we store the first and the last update. For performance reasons, we don't store all the updates. We could also store all the updates, but at the moment we don't.
Maybe it's good to look at the schema and look at some queries to see what that actually means with the time windows and the different time window buckets that we have, hourly, daily, and so on. Let me share my screen and I can show a little bit of stuff while you're talking about this.
Yeah, so this hourly asset price candle is a good thing. So for each asset, it has a from and a to timestamp. So this will be the start of the hour and the end of the hour. It has an open price. It has a close price. It has the low price and the high price. So basically, whenever a new asset update comes in, the first one will be the open price, and the last one of the hour will be the close price. And then we also compare if the price update that comes in is lower than the lowest or higher than the highest, and then we overwrite that. So, but that basically gives us gives structure to the price updates. And later, when we want to use use the prices to calculate fund values, asset values, or the total value of a fund that holds several assets, we have all the prices basically at the same time. We can just look at those price candles. What we call candles is probably better, actually, but would probably be a window would probably be the better name. But and then we basically have prices at the same time stamps.
So let's look, for instance, at asset again, Melon here in this case. So this is the Melon token, and then using derived from here we have, for instance, the hourly price history. Like these are the hourly price candles for that asset, hourly history, and let's order that by open time. From time, yeah.
Yeah.
Order direction scanning, and yeah, then you'll see here the open price of that of the, like this is the open price of that asset.
Yeah.
From like beginning of when we started tracking this, the first 100 records now. And these are predictable time windows. So that's really important, because that way we can very easily, we see like these were always 3,600 seconds, which is 1 hour. So that's very nicely predictable time windows for tracking this data. That allows us to really like easily query predictable slices of the history, knowing that these are always in the same intervals. Let me maybe explain why this is important. So when you are otherwise querying the first 100 asset price updates for asset A, if that asset has very frequent updates, that could be a time range of, let's say, 2 days, 3 days. If it has very infrequent updates, that could already be a month. By using these predictable time windows, we can much easier scope the data we are requesting across different assets, and then loop over that data to draw charts with much less effort on the data processing side after the fact.
We do that even also for fund states, hourly fund states actually. Yeah. A fund state changes when there's no investors, or when there's trades, or anything else happens in the fund, which is nothing to do with price updates. Using those hourly fund states and the hourly prices, it's very easy to calculate additional quantities on basically every hour. So then basically we have timed information for number of investors, number of shares, assets that the fund holds, and we can easily marry that with the asset prices that are in a way completely different data source, but they need to be kind of assembled. And so assembling that and doing those calculations, we do not in the subgraph, we do that externally. But by kind of, I think, so what we want to say is by storing the data in a intelligent way, it's afterwards much easier to do calculations on a kind of on a time series basis. And so we store data on hourly states or hourly prices, but we do the same for daily and monthly actually. So then we can also easily calculate daily values. So if you're looking at longer time scales, we don't want to, you're not concerned with what kind of happens intraday. You just want to know what the day close price was, or even monthly. If you're looking at hedge fund performance, typically you're kind of looking at monthly performance data. Yes, indeed. We don't need to do the daily thing. We have hourly data. So in principle, we could just query all the hourly data. But it's much simpler to query if we just need daily data. It's much simpler to query just
especially because the limit is 1,000 records
Yeah.
per query, right? So 1,000 days, that's already 3 years.
Yeah.
But 1,000 hours isn't.
Yeah, and also the filtering on a query is it's possible, but you can't do so kind of fine-grained filtering. I mean, if you do filtering, saying always give me the last daily, the last hourly history of a day, then that would also work, but
Yeah.
you can't do that. Yeah. So then kind of you need to be a bit imaginative, but kind of having set time windows is very important.
Maybe in comparison, because there's also the feature of querying historical data using the block filter, right? So
Yeah.
because you could actually filter the or display the representation of the data of the subgraph at a particular block. That's fine for doing debugging and yeah, just looking at the overall state of the subgraph at that particular block, but it's not useful for querying time ranges. So if you were thinking about using the block filter for traveling back in time or querying entire like data ranges, time-based data ranges, that's not a suitable feature to look for that. So yeah, tracking historical data is still that rests on your shoulders when defining that subgraph.
What are the drawbacks of using time travel queries?
It gives you the asset price at the given block, which is interesting. But you don't want to send dozens of queries where you always check and change the block number. You want to send one query that tells you, give me all the asset prices between timestamp A and timestamp B.
So if I wanted to get the price development between this block and the next block, I could let's say we do 1 million blocks. Okay, I could do such a query here. Obviously, that's not. Let's do that. You see, this is a way for querying 2 data points, but querying this repeatedly to get like 100 different data points spread out over a particular block range is obviously tedious. Now you could start messing around with the GraphQL syntax a little bit to make this look a little bit nicer, right? Oh, sorry. But still, it's just not convenient.
Yeah.
Right.
It is convenient for certain use cases. So for example, if as you said, for debugging, or if you want to go back in time, or you want to look at how your system, how the state of everything you are monitoring was in a certain block, then is certainly useful.
When querying the time series data, there's one interesting pattern that we use. So again, let's look at the prices for Melon. Let's look at the daily history. If you were to query the daily history between a particular date, start date and an end date, you might want to also load the last record in the previous time range, simply so that your chart doesn't start and suddenly comes out of the 0 range when running the data, right? So you might want to have like a little bit of an overlap, and that's quite simply possible. So here you get the daily history from, let's say, again, this time window that we started here from 2 months ago. So where from greater than this time window. And then we also, actually that's all, the first, let's say the first 100 days after that, okay? Or the first 100 records after that. And then from that we get the open timestamp. That's ordered also. So then you can alias that to the history, and then you can like the previous record would be where from is lower than, and then from that you get the opposite sorting, and you just get the first one. right? And then this is the history, and then the previous. Let's reduce it here. The previous record is basically the last record of the previous time window. Yeah, I mean, here you would then use the same approach that we talked about before. Right? You'd also have like a lower and upper bound simply to optimize the query performance. But this is basically the gist of it. For charting, we found that this is just nicer if you want to have nicely rendered charts that don't start at 0 or start out of nowhere. You likely want to include like the previous record outside of the range you're currently looking at. Same can be done by using the last record basically, so that also your chart doesn't suddenly drop to 0 at the end of the observed time interval.
Assembly script looks like TypeScript, and you kind of think it's very similar, and it is very similar, but it's just you have to be more precise. And you, as you said in the beginning, Sebastian, there's no kind of packages for doing a little bit more complicated things. So we wrote a few utility functions basically that we can use. Maybe let's go into the array thing, or
yeah, the array thing is a good one actually, because that also highlights the array problem that we ran into, you remember?
Yes. Yeah. So often you kind of want to you have an array and you kind of want to take something out of that array, or you want to add something into the array, and so we array diff and array unique, I think we're using quite a lot. Or you want to add, I mean, removing things from the array.
Now, this obviously, the removing things of the array using array diff, that's something we use quite frequently. One important thing to note here is it does like a direct comparison because it checks whether the value exists within the array. So this wouldn't work for a comparison of complex objects. This does work for strings and primitive numbers.
We use it mostly, I think we use it mostly for strings, for addresses, adding or kind of removing addresses from arrays, or adding.
Definitely IDs or references, updating state, filtering stuff out that was previously there. See also in comparison or in conjunction with a array unique. Yeah, or when new event comes in, removing something or adding something. Yeah.
Instantiating an array, you're kind of tempted to write a square brackets basically. Don't do that.
This bug is, by the way, fixed in the latest assembly script version, but the version that the graph currently is still based on, this is indeed a problem. It took us hours to figure this one out. So basically, there's this leaks, right? So don't define arrays like using the shorthand, because every time you do that, memory or somehow the memory representation, the memory pointer for this shorthand array leaks into the next cycle, into the next iteration. So the next time you will call array diff, this won't be a new instance of the array, but it will rather reuse the previous one. Not all cases, but in some. And it was really hard for us to debug because this occurred in some occasions and sometimes it didn't. But yeah, since then we are always using the long syntax new array. So another reason why we are using for loops and not map or filter or for each more frequently here is scope. Scope is not inherited into closures. So any kind of loop really, where you want to have, where you want to use values that you declared outside of the loop, if you were to use a closure function with a map function or for each or whatever, it wouldn't work. So let's just make an arbitrary array here somewhere. I want to get an array where all of the values that are left are only those that don't match the value 3 in this case, right? So I'm tempted to do this. And you could, for instance, say value doesn't equal my value. But that won't work because my value is not available within the scope of this closure function. Does that make sense? And that's just an assembly script quirk. Scope is not inherited into closures. We have some utilities also for string encoding, decoding. These are sometimes useful depending on what contracts you're interacting with. If there are strings or encoded strings in there that you want to decode, this can be quite handy. We have mathematical utils for big number and big decimal operations. So converting to a big decimal with a certain number of decimals. Min-max functions also quite handy. These exist for normal numbers natively in assembly script, but not for big decimal or big int, because that's simply a construct that's coming from the graph runtime. Average, median, again, the same stuff for big int, right? And then division that takes care also of cases where you're dividing by 0. Time operations. So again, what we talked about earlier with tracking time series, time window data. There's no date library in assembly script, and date isn't natively available. So we did a little bit of the poor man's date lib, really, because instead of doing all of the annoying and difficult calculation to figure out when a month begins or ends, like with leap years and all of that stuff, what we did, we just we just have a long range of timestamps for month begin times that we have in here. And then if you want to figure out what the beginning of a month is, we basically just loop through this array and find the first match. Yeah, it's just really lazy, but it works. Yeah, I mean, it's for a significant time frame between July 2015, which was the deployment of Ethereum, and then February 2032. So that should suffice for a substantial amount of time. Yeah. And then just some constants in here, some other time operations. So day open, day close times, minutes, 10 minutes, hours, months. Utilities for figuring out if something is in the same hour, same day, same month, and so on. Token utilities for safely fetching ERC20 token names, ERC20 token symbols, ERC20 token decimals, and so on.
Well, it's really great having you, Ivan and Sebastian.
Thanks for having us. Yeah, always a pleasure.
Thanks for having us.